fire hydrants. We all know they're useful for fighting fires, but they also have another purpose, and that is they're a way of finding out what's happening in the water distribution system. By conducting fire hydrant flow tests, we can tell something about the condition of the water distribution system. This video is going to cover several aspects of conducting and reporting fire hydrant flow tests. The first part has to do with the actual steps in conducting the test. This involves what you need to measure, what kind of equipment you need, and a discussion of some of the pitfalls that you need to avoid in conducting the test. The second part of the video is oriented towards the engineers who have to use this data. What kind of lessons can they learn from the kind of data they're getting? So the first part is oriented more towards people who are actually running the fire hydrant flow test. That's basically anybody, I guess, who realizes that this isn't just some short man with a red hat. My name is Tom Walski, and I work for the Corps of Engineers at the Waterways Experiment Station in Vicksburg, Mississippi. I'm going to be talking today about conducting fire hydrant flow tests and trying to make the most of the results you get from those flow tests. Fire hydrant flow tests are very important in that they give you a way to evaluate the strength and weaknesses of your water distribution system. There are really two parts to conducting this sort of test. The first part consists of actually making the measurements in the field. The second is using those results to predict what's going to happen in case of some emergency, such as a fire. This is a video about conducting hydrant flow tests, yet here I am sitting in front of a computer terminal. You're probably wondering what the connection is. Well, in the old days, when you ran a flow test in the field, all you could do with the results of that test was basically plug it into this equation here and have some idea of how much water you get out of the hydrants under some other residual pressure. That was about all you could do with it. But nowadays, with computers and better computer models of distribution systems, you can use the results of hydrant flow test to calibrate a model of a distribution system and then use it to play all sorts of what-if games. So basically, this is a limited way of being able to extrapolate the results of flow tests to other conditions. Computer programs are ways of extrapolating those results to an even wider range of conditions. Before we talk about what we're going to measure at a hydrant flow test, it's necessary to understand two terms, residual hydrant and float hydrant. The residual hydrant is the hydrant at which pressures are measured. The second type of hydrant is the float hydrant. At the float hydrant, only the discharge from the hydrant is measured. In some cases, there may be more than one hydrant that is flowed, but there's only one residual hydrant at which the pressure is measured. Now that we've defined residual hydrant and float hydrant, it's time to define some of the quantities that we're going to measure during the test. The first quantity is the static pressure, P sub S. This corresponds to the pressure at the residual hydrant when the hydrants are not flowing. So this is the pressure during normal water use at the residual hydrant. The second quantity measured at the residual hydrant is the test pressure, P sub T. This corresponds to the pressure at the residual hydrant when the float hydrants are open. It's important when you're measuring P sub T that you wait a little while to ensure that the surges caused by the opening of the float hydrants have dampened out and the pressure gauge is not moving while you're reading P sub T. The next quantity measured during the hydrant flow test is the test discharge. This is the sum of the flows at all of the float hydrants. Q sub T is not measured directly. Instead, the velocity head at each hydrant outlet is measured and it's converted into the flow from the hydrant using this formula, where h is the velocity head, c is the discharge coefficient for that hydrant, and a is the area of the hydrant opening. This equation is the same as the previous equation, except that the units have been converted into the kind of units we're used to working with in the field. For example, instead of the area of the hydrant outlet, we have d, the diameter of the hydrant outlet, and instead of the velocity head, we have p, the pressure corresponding to the velocity head. This equation is good for p measured in psi and d in inches to give you q sub t in gallons per minute. The discharge coefficient depends most heavily on the shape of the inside of the hydrant outlet. The most common shape we find is a smooth rounded outlet. In this case, the discharge coefficient is 0.9. Another common shape is the square and sharp inlet shape. For this type of shape, the discharge coefficient is 0.8. In some cases, the outlet of the hydrant actually projects back into the hydrant barrel. In this case, a good approximation for the discharge coefficient is 0.7. Another type of hydrant is the wet-barreled hydrant. In this case, it's very difficult to precisely know the discharge coefficient because the operating mechanism is actually part of the outlet. For wet barrel hydrants, or hydrants for which you don't know the discharge coefficient, it's possible to attach some type of pipe to the outlet to smooth out the flow. In particular, an underwriter's play pipe, which you see here, is a good way to have a known discharge coefficient. It happens to be 0.97. The problem in using an underwriter's play pipe, though, is that you don't use the diameter of the hydrant outlet, but rather the diameter of the tip of the play pipe as d in the equation we just showed you. During a fire hydrant flow test, it's necessary to measure really only three things. The static pressure, that is the pressure at the residual hydrant before any hydrants are open, the test pressure, which is the pressure at the residual hydrant when the hydrants are flowing, and then the sum of the flows at all the hydrants that are open. It's important to make sure that your residual hydrant is not the same hydrant that you're flowing. This is probably the most common mistake made during fire flow testing. The things you need to run the test are pressure gauges. You can buy the necessary gauges and hydrant cap fittings from any fire equipment or pipeline supply company. Some companies even sell complete kits with everything you need to run the tests. Usually, however, when you buy these pieces of equipment, you get some fairly inexpensive gauges which are not really all that useful if you want to get some very accurate tests. This one, for example, is graded every 20 psi, and you have to interpolate between those. Of course, this doesn't give you very good precision or accuracy. So the best thing to do is, when you buy this equipment, if they happen to give you some of these inexpensive gauges, is to just get rid of the gauge and go out and buy a good gauge. This is typical of the gauges that we use. They have gradation marks at every psi. They're ANSI type A gauges. With these, you can get some pretty good accurate and precise measurements. All you do is connect this thing to the hydrant cap fitting. Get it good and tight and attach to the hydrant, and this will give you the kind of results you'd like to get. While the gauge you just saw is useful for dry barrel hydrants, you could run into some problems when you're working with wet barrel hydrants, because as you shut a wet barrel hydrant, you tend to force water towards the gauge. This can peg out the gauge and damage it. So it's important when you're working with wet barrel hydrants to use a bleed valve on the cap gauge. This bleed valve must be open as you're closing the outlet on the wet barrel hydrant. This would bleed excess pressure and prevent you from damaging the gauge. Traditionally, you don't worry about the elevation of the residual pressure gauge while you're recording the results of the hydrant flow test. However, if you're going to use the results for model calibration, it becomes very important to know what elevation corresponds to the residual pressure gauge. So it's worth a little bit of time to determine the elevation. If you have good contour maps, say a 3-foot contour interval, you can read the elevation off the contour maps. However, if you're stuck in a situation where you only have 20-foot contour intervals, it's really worth the trouble to go back and try to get a better handle on the elevation. Usually, for example, manhole elevations are known. So you can shoot the elevation knowing the elevation of a nearby manhole cover. And this will give you a great deal of accuracy, because it's kind of silly to measure the pressure to within an accuracy of 1 psi, which is about 2.3 feet, and then add it to an elevation which is only good to say plus or minus 20 feet. So you'd like to get the elevation to an accuracy of plus or minus 3 feet if you're going to use these results for model calibration. In addition to measuring the pressure at the residual hydrant, we must also measure the discharge from the flowing hydrants. Since flow is volume of water per unit time, the most fundamental way to measure flow is to simply take a calibrated bucket and measure how long it takes to fill the bucket. Of course, those of you that have worked with fire hydrant flow tests know that a bucket like that would fill up very quickly and would be hard to hold while it was filling up. Therefore, we need some indirect way to measure the discharge from a fire hydrant. The way that's done usually is with a pitot gauge. A pitot gauge senses the velocity head that's coming out of the hydrant in the flowing stream, converts that reading to a pressure reading that you can read off the face of the pressure gauge. This is traditionally the way that fire hydrant flow measurements are made. Another design of a pitot gauge is this type, which can actually be clamped on the outlet of the hydrant. This has the advantage of having two scales in that it not only records the pressure equivalent to the velocity head, but also converts that reading into gallons per minute of flow. Now you have to be careful when you're doing this, because while the pressure readings are just velocity head, the gallon per minute readings embody two types of assumptions. That is, it assumes that the diameter of the outlet is exactly 2.5 inches and the discharge coefficient is exactly 0.9. This may not be the case for your situation, so you may have to correct the readings. Therefore, it's best to make sure that you record the actual pressure readings, even if you have flow readings recorded. The other thing to remember about these gauges is that flow is related to the square root of the velocity head. Therefore, for very small pressures, this gauge is very inaccurate, and it becomes very accurate up at the higher range. So you'd like the readings to be on the higher range of the gauge, which means that if the gauge is reading at the lower end, you probably need to replace this gauge with another gauge. While it's not absolutely necessary to record the information you see on the screen, it is very helpful to jot down the water levels on the tank, which pumps are running, and what the settings are and any pressure reducing valves that are affecting the test. This makes it very easy to go back and compare test results with tests run under different conditions. If you don't record this, you may have a problem later on in understanding why the results from two tests are different. Now let's go outside and run a test. First, you identify which hydrant will be the residual hydrant and which hydrants are the float hydrants. You would send the individuals to each hydrant. Now, at the residual hydrant, you take off the hydrant cap and bleed any debris or rust or sediment out of the barrel for a short period of time before you actually attach the cap gauge to the hydrant. Next, you actually attach the gauge to the hydrant, making sure that you've got it good and tight. Next, open up the hydrant. This time the pressure gauge should indicate the static pressure. Take a reading of the static pressure once you have the hydrant completely open. The pressure gauge should not be bouncing around too much. If it is, try to find out what's happening. Are pumps kicking on and off nearby, or is a pressure reducing valve opening and shutting? Usually though, the gauge should remain fairly stable within 1 or 2 psi. Once you've recorded the static pressure and are satisfied with the reading, it's time for the individual at the residual hydrant to contact those at the float hydrant to see if they're set up and ready to begin the test. Now let's see what's going on at the float hydrant. Upon arriving at the float hydrant, the individual who's going to be conducting that part of the test first assesses the area and selects the outlet to open that will cause the least amount of damage due to flooding and erosion. He then removes the cap from the hydrant outlet and bleeds any debris or sediment out of the hydrant lateral and barrel. This is done to prevent any debris from flying out of the hydrant outlet and hitting the gauge and damaging it. It's amazing some of the things that children and vandals will put inside of a hydrant. Once he has flushed out the hydrant barrel, it's time to bring out the pitot gauge. In this case, he's going to be using the clamp-on gauge. It's important to clamp it on tight and as close to the center of the hydrant outlet as possible. Once the pitot gauge is in place, the individual at the float hydrant contacts the individual at the residual hydrant and indicates that he's ready to start the test. The individual at the residual hydrant then decides when it's time to begin the test. He then contacts the person at the float hydrant and indicates that it is time to start. The person at the float hydrant must open the hydrant very slowly. It's very important not to cause abrupt changes in velocity in the water distribution mains. Therefore, don't open the hydrant quickly. Open it very slowly. The person at the residual hydrant needs to control the test because in some cases you may have several individuals opening hydrants and you don't want them to be opening them simultaneously. Instead, you'd want the hydrants to come online one at a time. And the individual at the residual hydrant is in the best position to decide when it's time to open up another hydrant. Once the hydrant is completely open, the individual at the float hydrant will take a reading of the flow, which actually is a reading of the pressure head on the pitot gauge. Once he takes this reading, he radios it back to the person at the residual hydrant who will record it. It's also safe for the person at the float hydrant to write down the reading as well. Now remember, if several hydrants are involved in a test, that the flow at each hydrant is going to change depending on which other hydrants are open. So the individual at the residual hydrant needs to notice when he has a reading from a particular hydrant whether this reading corresponds to 1, 2, or more hydrants operating. When the individual at the residual hydrant is satisfied that the flow test is complete, he will signal to the person at the float hydrant to shut off the hydrant. Remember, just as you had to open the hydrant very slowly to prevent any surges in the distribution system, you also need to close the hydrant very slowly. The last few turns of the operating nut are especially important. Make sure that you do them slowly, or even stop periodically while you're shutting off the hydrant. The individual at the residual hydrant will be able to tell if one of the flowed hydrants is being shut too quickly, because he will notice the indicator on the gauge jumped rather abruptly when the pressure surge from the closing of the hydrant reaches the residual hydrant. To get an accurate reading of the pressure at the residual hydrant, it's only necessary to open the hydrant a crack, but you shouldn't do this because there are drain holes in the bottom of the hydrant that remain open until the hydrant is wide open. So if you only open the hydrant a crack to read the pressure at the residual hydrant, you'll be causing water to flow through the bleed holes and undermine the hydrants, as you see here. During a hydrant flow test, you should expect to get several hundred to over 1,000 gallons per minute out of a flowed hydrant. If you're only getting 100 or 200 gallons per minute out, as you see here, it's usually an indication that something is wrong during the test. One of the common problems is a great deal of tuberculation or scale inside the pipes. This tends to reduce the carrying capacity of the line. This type of problem usually shows up fairly gradually. If the loss of flow from the hydrant occurs rather abruptly in time, it's probably due to someone having left the valve closed or partially closed in the system. You need to go out there and find that valve and make sure it's completely open, because gate valves in the distribution system are supposed to be open. Okay. Before you go out and run the test, it's good to plan which hydrants you're going to open, which hydrants are going to be the residual hydrants. You may not always be able to do this exactly, because you may find that one of the flowed hydrants is in an area that might cause some damage, but it's good to plan before you go out to the field. Before you go out to the field to conduct the hydrant flow test, you need to look at the distribution maps, because the hydrants are the only thing you see above ground, yet a lot of things can be going on with the water mains underground that could cause misleading results. For example, some of the things you might find on the map are the fact that you may have several pressure zones in your system, and that in the area in which you're running the test, there may be mains with two different pressure zones, even in the same street. What this causes is a misleading result, because you may be flowing hydrants in one pressure zone while your residual hydrant's in another pressure zone. The results from this will be misleading. Hopefully you can recognize it in the field, but it's better to plan beforehand so that that doesn't happen. Another potential problem occurs when you have two mains in the street, say a small distribution main and a large transmission main, and some hydrants may be on the small main and others on the large main, and they're not connected for, say, several blocks. Again, here you can have misleading results if you're not careful. So before you go out to run a test, look at the distribution map to get an idea of what kind of pipes are underground, because you really can't see them once you get out to the field. You also need to be conscious of the fact that a hydrant flow test tends to stir up any rust or sediment that might be lying in the bottom of the pipes, and this deteriorates water quality. If there are people out there who will be affected by this change in water quality, such as laundries or hospitals, it's worthwhile to notify them about what you're going to be doing and when you're going to be doing it, so that they can take steps to minimize the impact of your test on their operation. It's just good public relations to let people know what's happening rather than surprising them with poor quality water. Always remember to be careful and considerate when you're running the fire hydrant flow test. You're usually doing these tests when you're working in traffic, so be very careful before you step out in traffic. Don't be afraid to put up some cones or barricades to protect yourself. Also remember that the flowing stream can damage a car. If a car drives through it, it can actually put a little dent in the side of a car. Remember, when you're removing a cap gauge from a hydrant, that if the hydrant's still pressurized, that gauge can fly off and cause a lot of damage. So always look at the face of the gauge to make sure there's no pressure on the gauge when you're removing it. Also, a flowed hydrant can cause flooding damage. Please be considerate of your neighbors. and water hammer caused by quickly shutting off a hydrant can damage the distribution system. So the thing to remember when you're doing this type of work is be careful and be safe. Before you go to the field, it's also very important to make sure you have some type of form or checklist to make sure you record all the information you need. It's very frustrating to come back from the field and find out that you did not record something. I suggest that you take the time to prepare some type of general hydrant test data recording form. We have an example of one that we use in our work. It's published in Corps of Engineer Technical Letter 1110-2-297, and it has blanks for the kinds of information you need to be sure you collect while you're out in the field. Such things as the residual pressures with no hydrants flowing, one hydrant flowing, the kind of information that you need to run a good test. Okay, now let's run some tests. Well, buddy, that ends the first part of the fire hydrant flow test video. Now we should all know the basic steps in conducting a fire hydrant flow test. Those folks who are only going to conduct the test can turn off their VCRs now, while the engineers who are going to be using the data may want to stick around and watch the rest of the video. You know, it's okay to talk to fire hydrants. The time you need to get concerned is when they start talking back to you. Now, what do you do with the data once you've run the hydrant flow test? Well, what you have from the test are really just 2 points. You have the pressure corresponding to zero hydrant discharge and the pressure corresponding to some known discharge Q sub T. In this case, the static pressure is 75 psi and the test pressure for a hydrant discharge of 600 gallons per minute is 50 psi. However, you're not only interested in the discharge at 50 psi, you want to be able to extrapolate the results to other pressures. Usually you want to be able to extrapolate to find the discharge at 20 psi. The intuitive way of doing it would just draw a straight line, but you have to remember that flow is related to the square root of the head loss in the line, which means you don't have a straight line but a curve. Which of these curves is correct? This is the equation that's traditionally used to tell you which of those curves is correct. With the results of the flow test, you can insert any residual pressure, P sub r, into this equation and determine an approximate discharge from the hydrants at that residual pressure. That discharge would be Q sub r. This equation has been used by engineers for many years for evaluating the strength of the water distribution system. It's also possible to rearrange the equation and predict the pressure for any given discharge from the hydrants Q. This graph and equation shows how you can determine the discharge at 20 psi given the results of a hydrant flow test. You can do it either graphically or using the equation. In this case, the discharge at 20 psi is 918 GPM. A common mistake when conducting fire hydrant flow test is to not open up enough hydrants to get a significant drop in pressure at the residual hydrant. You should get a drop of at least 10 psi at the residual hydrant. preferably you should have 20 psi or more drop. The problem is that if you don't get enough of a pressure drop and you try to use the results to extrapolate down to 20 psi, a small error in reading any of the gauges will be magnified. For example, in this case, the pressure only dropped 5 psi, and when you try to extrapolate those results to what the pressure would be at 1200 GPM, all you can tell is that it's going to be somewhere between 20 psi and minus 5 psi. That's not a very accurate way to do things. You need to open up more hydrants in this situation so that you could pull the pressure during the test down to about 50 psi. There are some problems in using that traditional equation for predicting discharge at any residual pressure. The first is that it assumes that the pressure under static conditions is the same as the pressure at nearby tanks. A second and more subtle problem, it occurs when you run the test near a pressure reducing valve. If, for example, in this test we show you drop the pressure down to 50 psi during the test, you would tend to extrapolate those results and predict a slow of about 800 at 20 psi. However, if there's a PRV nearby and it opens at 40 psi, connecting the area you're testing with a higher pressure zone, you could possibly get significantly more water during an actual fire due to the action of the PRV. So you need to be aware of when a pressure reducing valve could influence the results of your tests.
You're wondering why I'm leaning up against this pump when we're really talking about hydrant flow tests today. Well, as you know, what's happening at pumping stations has a lot to do with the resultant tests. Yet you can look at the results of hydrant tests run by some people and there's no indication of whether pumps were on or how many pumps are on or which pumps were on. This is unfortunate because it renders the results of these tests less useful for calibrating pipe network models. What you need to do is know which pumps are running when you're conducting the test. This is very important information and it's very easy to get. Also, you'd like to know what kind of pressure is being put out by the pumps during the test. In particular, you want to be sure that the pump isn't dropping its pressure when you open up the hydrants. For example, if a pump is already pretty far out on its head characteristics curve and you open up the hydrant, what's going to happen is that the pressure at the source will drop. Now, if you did not know that this happens, you might think that the distribution mains were losing its carrying capacity when really you were overtaxing the pump that was on. What you want to do during a hydrant flow test usually is to imitate what would happen during a real fire. Therefore, you want to turn on the pumps that would be on during a fire. So if the head at the pumps drops a lot during a test, it usually means you don't have enough pumps on. So you usually, during an actual fire, turn on another pump or maybe even two more pumps. So for the best results of the test, corresponding to what would happen during a fire, you want to have as many pumps on as you would during a fire. Now for model calibration, this isn't always necessarily true. You may want to calibrate the model, for example, for the case where all the pumps are off and the system is relying on a tank, as it would during a power outage. So think about what you want the pumps to be doing when you're running the test and have the pumps doing that and find out just what's happening to record it for the results of the test.
Some people conduct the fire hydrant flow test, calculate the discharge at 20 psi, write that result on a piece of paper, and the results never see the light of day again. Actually, they're losing an opportunity to get a feel for what's happening in their distribution system over time. By conducting the tests year after year and saving the results in some logical form, you can find out long-term trends in the distribution system. If the fire hydrant discharge is gradually dropping off over time, you can expect a problem in loss of carrying capacity in the mains or just generally higher water consumption by other users around the hydrant. If, on the other hand, the hydrant discharge drops off rather abruptly, you ought to first look around and see if the pumps were running correctly that day and the water tank was actually in service. And if those things are true and the system was behaving normally, you can usually expect to find a closed valve somewhere around the location of the test when the results drop off abruptly, as this shows. Well, we're done with the flow test, and here I am back at the computer terminal again. Now is the time where we have the opportunity to do a lot more with the results of the hydrant flow test than simply plug them into an equation and predict the discharge at 20 psi. The first thing you need to do is to save the results. It doesn't really matter if you write on a piece of paper or store them on the computer, but nowadays there are some nice features in computer databases and spreadsheets where you can take the results and store them year after year, and then you can go back and look at the results. How did they change with time? What are these changes in time telling me about what's happening to the distribution system? If all you were going to do, though, with the results of the test is simply store them on the computer, the computer wouldn't be worth the investment in the computer. Instead, the real power of the computer, though, is when you can take the results of the flow test, use those results to calibrate a computer model, and then use the model to do more things. You see, a computer model is very easy to calibrate if all you do is observe normal operating pressures. But if a model can be calibrated for normal operating conditions and calibrated to reproduce the results of a flow test, you could have a lot of confidence in it. It's a very credible model. And with that model, you can now play these what-if games. What if the fire happens when the pumps are off due to a power outage? What if the fire happens if the tanks are empty or very low for some day? You can't really do this out in the physical world because you'd be interrupting someone's services. But by getting the data from the field and then taking it back and combining them with the capabilities of a computer model, you can do so much more than you can with just the results of the test as we used to be able to do in the old days only. Well, that wraps up our video. Now it's time to go back and review some of the most important points we've made during the body of the video. We discussed the difference between the residual hydrant and the flowed hydrant. We learned about selecting the right pressure gauges for the test and how to read the hydrant discharge. We learned how to use a formula to calculate the discharge of any residual pressure, and we discussed the effect of pumps on the test. Finally, we talked about using the hydrant test data in computer modeling. Well, I hope that this video is going to help you do your job better in conducting fire hydrant flow tests and using the results. See, there's a lot you can learn from one of these fire hydrants.
Ouch. Watch it, Buster. Hey, wait. You forgot to put my cap back on. Oh, no. Here comes a dog.